Hi all, welcome to the lecture series on Aerospace Propulsion. Today the topic which we are going to discuss is thrust developed by a rocket. Okay, coming to the overview of today's presentation, we will discuss the thrust developed by a rocket, thrust coefficient and thrust correction coefficient. These are the three topics which we are going to discuss in today's lecture. Coming to the thrust developed by the rocket. So, first go through the diagram. Here we have taken the control volume containing a stationary rocket. Okay, see here, this is the rocket actually. This is the rocket. Okay, and it is fixed to a, this rocket is fixed to a support. Okay, this is a support and this rocket is fixed here. Alright, so whatever the thrust developed by a rocket, okay, the thrust developed by a rocket will give a force on this support. Okay, so whatever the force acting on the support is nothing but the thrust developed by the rocket. The reaction force developed by the momentum of gases will act on the fixed support, and that is nothing but our thrust developed by a rocket. Here coming to the parameters. So this is the control volume A, B, C, D. So this is the control volume here we are considering in this diagram. And next EF, okay, EF, GH is the dotted lines here we have taken to calculate to differentiate the rocket nozzle exit and remaining control value, right? So Vj is the velocity of the gases, and here the Pe is the exit pressure at the nozzle exit, Ae is the nozzle area, exit area, nozzle exit area, and Pa is the ambient pressure, it is in the atmosphere. Okay, and we can also consider in the control value. And next this is the Ae, okay, dashed line, which is equal to the GH equal to EF here, GH is equal to EF. Next, the pressure in the chamber is given as PC. Okay, and this is Ae. So in order to calculate the thrust developed by a rocket, first we need to find the rate of change of momentum produced by the gases. Okay, this rate of change of momentum produced by the gases is done with the help of Vj. M dot is nothing but M dot Vj. M dot is the mass flow rate of the gases which are leaving the nozzle, and Vj is the velocity with which the gases leaving the nozzle. Okay, this is nothing but the momentum exerted by the gases at the nozzle exit. Okay, so the force M, first the force Fm is nothing but the rate of change of momentum of the jet. Okay, that is given by Fm is equal to the force due to the momentum is nothing but Fm is equal to M dot into Vj. Next, unbalanced force. There will be some unbalanced force at the nozzle exit due to the pressure difference. See here the pressure at the exit. Suppose if I consider this is the control value here. If I consider this is the control value. Okay. So the pressure at the exit is PE, right? And the ambient pressure is PA. The both pressure sometimes they can be equal, sometimes they may not be equal. Okay. Sometimes exit pressure PE will be greater than ambient pressure. Sometimes it will be less than ambient pressure. So based upon the expansion of the gases happens in the nozzle. We have already gone through this in the nozzles, right? So whatever the pressure difference, the force due to the pressure difference at the exit, at the nozzle exit is nothing but the resultant pressure. So that is given by pressure into area, the resultant pressure into the area of the nozzle at the exit. So the pressure difference is given by PE minus PA. PE is the exit pressure minus ambient pressure. So this is nothing but the resultant pressure acting at the nozzle exit into the area. Pressure into area will give you the pressure force, which is nothing but the pressure force due to the pressure at the nozzle exit. So there are two forces, right? One is due to the momentum and one is due to the pressure difference. So if we apply the sum of the forces acting along the jet axis in the control volume, if you calculate the sum of the forces, then we will get F is equal to the force acting on the support F is equal to, one is due to the momentum of gases m dot Vj, and one is due to the pressure, that is Pe minus Pa into Ae. These are the two forces acting on the exerted due to the momentum of gases. So using the value of m dot and Vj in the above equation, what we already derived the equation for mass flow rate through a nozzle, and also we have derived the equations for velocity of the jet at the exit in the previous lectures. So we have to substitute that m dot and Vj, okay, m dot and Vj, then we will get the basic formula is, I am writing the basic formula here, F is equal to m dot Vj plus Pe minus Pa into exit area Ae. Okay, so here we are substituting m dot and Vj, substituting m dot and Vj equations which are developed in the previous lessons in this above equation. Then what we get is m dot. Okay, so the final equation will be F is equal to under root gamma Pc At by under root R Tc into 2 by gamma plus 1 into over gamma plus 1 by 2 into gamma minus 1 whole under root of 2 gamma RTC by gamma minus 1 into 1 minus Pe by Pc whole to the power of gamma minus 1 by gamma. So this all this term what we get is after substitution of this m dot and Vj in this equation 1. Okay, so further we can simplify this. This is a final equation we get. So the above equation can be again rearranged. So if I rearrange this gamma and I can send this root gamma into this, okay, and RTC, here we have one RTC term like under root R and under root Tc, here we have gas constant and we have temperature at the chamber, and here we have one equation like one term with the gammas in terms of gammas. So we can send all these terms and we can rearrange these terms. Okay, after rearranging the terms we can bring this PCAT out. Okay, the PCAT will be outside and under root gamma. So gamma under root RTC we will send inside. These two terms will send inside. Okay, then it will become PCAT under root 2 gamma square by gamma minus 1, 2 gamma square by gamma minus 1 into 2 by gamma plus 1 whole to the power of gamma plus 1 by gamma minus 1. And here this term will be same, 1 minus Pe by Pc whole to the power of gamma minus 1 by gamma, and this term also as it is. The only thing changes with this and this term. Okay, and if I take Pc, okay, if I take Pc common here, then what we get is F is equal to Pc into At, okay, under root of this total term plus Pe by Pc minus Pa by Pc into Ae by divided by At, right. So the final equation of thrust developed by a rocket is F is equal to PCA2 into all this term which is in the curly bracket, which all this if you observe this total equation, this is in terms of gammas, okay, and this is Pe by Pc ratio, exit pressure to the chamber pressure ratio, and here also exit pressure to the chamber pressure ratio, and this is ambient pressure to the chamber pressure, and this is exit to throat, okay, exit to Ae by At area ratio. So the term which is in the curly bracket here, whatever the term we have kept here in the curly bracket except from this PCAT, which is denotes the application of the force. Okay, this PC is the pressure and area, so that is the actual force, and whatever the term in the curly bracket which increases the force value generated by the nozzle. Okay, so whatever this term which is amplifying the force which is generated by the chamber pressure acting on the nozzle throat, right? So this is called it is called ideal thrust coefficient, which is called ideal thrust coefficient, and this symbol for this is CF. Ideal thrust coefficient is denoted as CF. And next, the equation for the thrust can be rearranged by substituting this CF here. Then what we get is F is equal to CF into PCAT. So the maximum thrust coefficient obtained when PE is equal to PA, and that thrust coefficient we get is called optimum thrust coefficient, and the symbol for that is C naught into F. So here the exit pressure, if I consider the nozzle, rocket nozzle, okay, the exit pressure PE and ambient pressure PA. Okay, if PE is equal to PA, then this term will become 0. Okay, the term will become 0 and the thrust will be maximum. Okay, so that's why when P is equal to PA, whatever the thrust coefficient we get in this curly bracket, that will be called as optimum thrust coefficient. Okay, that is CF naught. Okay, if I substitute, if I write the equation, okay, CF naught is equal to what? 2 into under root 2 gamma, and if I substitute P is equal to PA here, and if I write the equation of CF, this curly bracket, the term in the curly bracket, then you will get this term, this total term will be equal to 0, and you will get only this term. Okay, so this term will be considered as CF naught. This term will be considered as CF naught, that is equal to root 2 gamma 2 by gamma plus 1 whole to the power of gamma plus 1 by 2 into gamma minus 1 into 1 by under root gamma minus 1 into 1 minus PE by PC whole to the power of gamma minus 1 by gamma. So this term is ideal thrust coefficient. Okay, here you can also go through this graph. Okay, here this ideal thrust coefficient depends on the ratio, pressure ratio. Okay, this ideal thrust coefficient is depending on P. See here, it has PE by PC, exit pressure to the chamber pressure ratio. Okay, all remaining terms are gamma, gamma here, gamma, here also I have gamma. So all remaining terms are gamma. The only term is PE by PC here. That means the extent, if you consider the rocket, so the chamber pressure is PC and the exit pressure is PE. So to how much extent the pressure is decreasing, to how much extent the pressure is expansion, the gases expansion is going on, that is deciding the value of optimum thrust coefficient. So if the PC by PE, okay, this value is increasing. Here you can see this optimum thrust coefficient is decreasing. This optimum thrust coefficient value is decreasing here. Depends on PE by PC. This is PE by PC. Okay, here if you see PE by PC, if the gases are expanded more, then the PE value will decrease. If the gases expansion is good, then PE value will be less. Okay, so then PE by PC value also decreases, right? So the same thing you can observe. Here the PE by PC value is less, so you will get here you are getting maximum thrust coefficient. As the PE by PC value increases, okay, as the PE by PC value increases, that means the exit pressure is more when compared to the that value of PE is more, right? It is the increases. That means the gases are not expanded properly. So at that times you can see the optimum thrust coefficient is decreasing as PE by PC value is increasing. Okay, so to get maximum thrust, our requirement is PE by PC should be as much less as possible according to the optimum condition, not more than that. Even though if the PE by PC is very less, then also there will be some losses due to the over expansion, shock waves will form, that also affects the final total performance. Okay, next the velocity Vj, mass flow rate M, characteristic velocity C star, thrust F, thrust coefficient Cf, and optimum thrust coefficient is C naught F, were derived by assuming the perfect gas. Whatever the equation we developed, that is by assuming the perfect gas, steady and one-dimensional flow with isentropic expansion of the gas in the nozzle. These are all the conditions. One is perfect gas, we are considering the gases are perfect gases, and it is a steady one-dimensional flow. But and next, isentropic expansion happens in the nozzle. The corresponding to the ideal conditions, the departure of this ideal condition would lead to a reduction in the performance of parameter and an efficiency factor called C star. Okay, but actual conditions, whatever the equation developed till now, by considering these gases like perfect gas and one dimensional flow and isentropic expansion in the nozzle, but in real case it is not 100% possible. So that's why there will be some drop in the efficiency. Okay, that efficiency also we have to calculate that efficiency factor. Okay, that is a C star, efficiency of C star. Okay, so this efficiency factor, okay, this efficiency factor is given as C star actual characteristic velocity, actual characteristic velocity to the ideal characteristic velocity. So this is giving you the efficiency factor. And next there is one more factor, thrust correction coefficient. Thrust correction coefficient. It is defined to the it is defined to relate the actual thrust. Okay, actual thrust with respect to the ideal condition, the thrust developed by the ideal conditions. So that is given by this thrust coefficient. Okay, the thrust correction coefficient is given by CF actual thrust coefficient divided by ideal thrust coefficient CF. Okay, this is called thrust correction coefficient. The ratio of actual thrust coefficient divided by ideal thrust coefficient is called as thrust correction coefficient. And coming to the characteristic velocity, the characteristic velocity is given as C star is equal to PC by AT divided by m dot. From this we can write F is equal to CF into PC AT. CF is equal to F is equal to CF into PC into AT, right, from the above equation which we have derived. And next from this we can also write the equation for specific impulse. So if you calculate a specific impulse, so specific impulse general formula is F by m dot, thrust developed by mass rate of the propellant supplied. So this specific impulse can also written in terms of C star here, that is C star. Okay, F is CF PC AT. Then if you substitute that, then you will get specific impulse ISP is equal to C star into CF, C star into thrust coefficient. So specific impulse is a direct parameter which enables us to assess the performance, right. So this is about today's topic, thrust developed by a rocket, thrust coefficient and thrust correction coefficient. Thrust developed by a rocket, we have derived the equation which is depending upon the m dot Vj and the pressure difference Pe minus Pa into Ae. So pressure force and momentum force, and this thrust coefficient is a difference between the ideal to the actual exhaust velocity, which will depend upon the expansion process. And this thrust correction coefficient, it depends upon the actual thrust coefficient and ideal thrust coefficient. So these are about the topics which we have discussed in this lecture. Thank you.